GATE 2024, question 55. Methane combusts with air in a furnace with this reaction. So let's say this is my furnace and there is a burner here. In fact, there are several burners. I'll show in the actual process application later on. The heat of reaction is given for this reaction, this burning reaction here, and is assumed to be constant independent of temperature. That's the assumption. The furnace is well insulated, so there is no heat loss from the furnace, adiabatic, and no other side reactions occur. So that's definitely an assumption. All components behave as ideal gases. So with constant molar heat capacity, so all gases means, see here, pure methane is entering. There's a methane burns here, and here air is entering, and it is saying that oxygen is 20% standard, nitrogen 80%, and 20 more percent oxygen, 80 more percent nitrogen. And this mixture enters the burner at 50 degrees Celsius, slightly preheated, and this air fuel mixture comes in. So this is coming at the final temperature T, which we have to calculate. And the reactants are of course methane, oxygen, and nitrogen, and the products are unreacted methane and unreacted oxygen. Nitrogen, of course, what is an inert, so whatever is here that goes directly here, and carbon dioxide and water. So it's saying that the molar specific heat of all these compounds, that is methane, oxygen, nitrogen, carbon dioxide, water, etc., they're saying that assume all of them to be constant and equal to this. Of course, this is an assumption. Air, of course, considered as 20 more percent oxygen, 80 more percent nitrogen. The air fuel mixture enters the furnace at 50 degrees Celsius. The methane conversion X varies with the air to methane ratio. So this is normally called the burner performance curve, which is controlled by chemical engineers using a damper or a fuel valve, where R is called. We'll first see what is RS called. RS is the stoichiometric air to methane mole ratio. See, stoichiometric oxygen to methane ratio is 2, of course, and air to methane ratio of we can calculate, because once you calculate oxygen to methane ratio, and we know there are 20 more percent of oxygen in 1 mole of air, so we can easily calculate the value of RS. We'll show that just very quickly. And R is equal to 1.0, so we add 5% extra sum. So typically between 5 to 15% of excess than the theoretical requirement is fed into the burner. That's the standard procedure. Okay, let's see a typical chemical engineering application. This is a very important industrial reaction, because the fired heaters, these are the typical fired heaters in the industry, as you can see that picture here, or the reformer furnace, and sometimes the steam boilers and the hot air dryers. They use a natural gas, which is mainly methane, is burned to heat crude oil, naphtha, air, etc. So as a typical diagram, natural gas enters here. So it is a natural gas plus air mixture enters here, and the flue gas comes out from here. So that's a typical flue gas composition, and the process fluid, which is might be the hydrocarbon, crude oil, or the naphtha, enters here, and the heated oil comes out from here. So now let us look at the solution of this problem. Let us take the basis as 1 mole of methane entering. So this is 1 mole of methane entering. If we take that as a basis, then RS is the stoichiometric air to methane mole ratio. So we can say it's a stoichiometric oxygen to methane ratio is 2. So this is mole of air, 1 mole of air per mole of oxygen. So therefore, stoichiometric air to methane ratio would be equal to 10. Okay, this is 2 moles of oxygen per mole of methane, and this is 1 mole of air per 0.2 mole of oxygen. So that makes it this equal to 10. And R is given as 1.05 of RS. That's given. So the R is equal to 10.50. So for each mole of methane, 10.5 moles of air entering this burner. Okay. Now, one interesting thing is that because of this reaction, as you can see, 3 moles of the reactant, 3 moles of products are formed. So, and also we can see that nitrogen is the inert, so it goes in as it is. So there is, due to this reaction or due to the burning of this methane, there is no change in the number of moles of the number of moles. That means the number of moles going in, which is equal to 11.5 mole, is the same number of moles going out, 11.5 mole. How 11.5? Methane is going basis as 1 mole and air is 10.5 moles. This 10.5 moles of air entering per mole of methane. So total. Okay. All right. Now let us do the energy balance. Because to find out the exit temperature, we have to find out the exit flue gas temperature in degrees Celsius. So this temperature we have to find out. The inlet temperature is 50 degrees Celsius. Okay, we know the energy balance is this one right here. Since this is adiabatic, it's already said, so Q dot would be equal to 0. Ws is equal to, and if there is any shaft work, there is no shaft work, so that would be equal to 0. Now, this is the total number of out is a, for each species, the number of moles going out, like for carbon dioxide, water, oxygen, night, etc. And this is the molar specific enthalpy. That means the kilojoule per kilomole of that particular species multiplied by the temperature difference. So that's what it is. So same thing for E, and this xi is of course the extent of reaction, and delta H0 is the heat of reaction that is given, and we are assuming that to be independent of temperature. So there is no change in number of moles due to reaction. What we have seen, this is equal to, so this is equal to this. Okay. And Cp in is Cp out. So that's given. The conversion is, of course, we know is given by this reaction. So for methane, this would be the number of moles of methane entering, number of methyls going out divided by number of moles entering, and this value is 0.9432 we have calculated. How we have calculated there? Because this x value is calculated from this relationship which is called the burner performance curve, where this is used by the normally by the engineers. This is set by using the damper of the fuel valve. They calculate the value of the conversion using the per burner performance curve. Since we know the value of R, which is this one right here, since we know the value of RS, which is given here, so from this equation we calculate the value of X, which is the conversion. All the detailed calculations are of course shown here. So we know the value of the conversion, and xi is given by Ni, that is number of moles, let's say methane going out, not in, going out, minus number of moles methane entering divided by nu I, which is the stoichiometric coefficient. Now for stoichiometric coefficient, of course, for this reaction, stoichiometric coefficient for methane is 1, stoichiometric coefficient for oxygen is negative of 2, and stoichiometric coefficient of carbon dioxide is plus 1, and stoichiometric coefficient of water is plus 2. Right? So since we are dealing with methane, so this value is negative 1. If we do the calculations, we know that this is the value, we get the value of xi. That means the extent of reaction is the same as the conversion, is 0.9632. So let's do it here. As we said, this is equal to 0, this is equal to 0, so this is 0. N dot out is 11.5 total moles, and each has the same specific heat, so we multiply 44, and T out minus T reference. This T reference can be any temperature, let's say 25 degrees Celsius or whatever. And same thing, this is for inlet, again for number of moles in coming in is 11.5 multiplied by 44, and this is relation, and this is the conversion, that's the extent of reaction xi. So this is xi, and this is the heat of reaction. This value is given, and this factor 1000 is because it is given as the is given as the kilojoule per mole of methane. Every joules, this is in terms of joules, so we have to multiply this by 1000 to bring parity here. So that's where this 1000 is coming in. If we do the calculation, this is the temperature. So this is my answer, that is 1725.13 degrees Celsius.